In our first example for section 3.1, we're going to look at a limit that doesn't exist. As a quick reminder from the reading, if a function, let me just say f, approaches two different complex numbers, so they have to be different, say L1 and L2, and they're not the same, and they're approaching, the values are approaching that along two different input curves. You should think about this input curves as just paths. And usually your path starts somewhere and then ends at the point you're taking the limit at. Then the limit cannot exist. Okay, so this is not a new idea. In multivariable calculus, you looked at such things. If you could approach along two different, say, lines or more generally curves, and you got two different answers, then the limit doesn't exist. And of course, with real numbers, there's really only left and right hand limits. And so the real analog is the limit as you approach from the left and the limit as you approach from the right. Either one of them doesn't exist or they both exist and are different. Okay, so that's the real analog of this. So just a quick reminder that we have our approach paths in complex land, and that's how you show that a limit doesn't exist. So we're going to use that. We're going to look at a certain function. We're going to look at the function z over z bar, and we're going to look at the limit as z goes to 0. Now the general rule is if your functions are nice enough and you can just plug in 0, you plug in 0. Can't plug in 0. Our functions aren't well, they're nice, but we can't plug in 0 here. So what we're going to do is we're going to approach 0 along two different paths and see if we can learn something. Let me also notice real quick before we do that the reason why we're going to try to prove the limit doesn't exist, aside from the problem, the example telling us it doesn't exist, is just because there's not any clear algebra here that we can do to simplify this to maybe try to plug in 0. And so maybe it doesn't exist, maybe it does. We don't know. But we do know that if we try some approach paths, we can try to learn something about whether or not it exists or not. So I'm going to give you two common approach paths to 0. These aren't the only ones, but these are ones that are often used as the first attempt. You can approach along, let's use a more harsh color here. We can approach 0 along the real axis. So here's our approach curve C1. And we can also approach 0 along the imaginary axis. So there's going to be our approach curve C2. So that is, along C1, we are looking at points x plus 0i, where x is a real number. And our approach curve for C2 is going to be 0 plus iy, where y is a real number. All right. And as z goes to 0, if we're on these curves, this is what we're going to do is we're going to place the limit with x goes to 0. And as when we're along the curve C2, as z, we look at points like this, as they go to 0, y is going to 0. So what we're going to do to try to compute this limit is we're going to approach along C1 and see what happens. So we said that limit x goes to 0 instead. Z over z bar. So that's x plus 0i over x plus 0i bar. That's limit x goes to 0, x over x, because we conjugate the imaginary part. There's no imaginary part. And now we can do some algebra. That's 1, and we get 1. All right, so let's pocket this. This is our limit if we're approaching along the real axis. And now let's approach along the imaginary axis. So that's limit y goes to 0, 0 plus iy is 0 plus iy bar. So now the conjugation does something. So we get iy over negative iy. Nevertheless, these cancel, and we get the limit as y goes to 0 of negative 1, which is negative 1. And that's our value, our limiting value as we approach along the y-axis. So since 1 is not equal to negative 1, this limit cannot exist.